Have you ever seen a baby photo of the universe? It sounds impossible, but we actually have one. It's called the Cosmic Microwave Background, or CMB, and it's one of the strongest reasons scientists take the Big Bang model seriously. Because the CMB isn't a theory, it's something we can measure. Let's break it down in a clear way. First, what is the CMB? Imagine the universe extremely early on, hot, dense, and filled with a glowing soup of particles and light. In that early universe, light couldn't travel freely. It was constantly bouncing off charged particles, like a fog so thick you couldn't see through it. Then, about 380,000 years after the Big Bang, the universe cooled enough for electrons to join with nuclei and form neutral atoms. When that happened, the fog cleared. For the first time, light could move freely across space. That light is still traveling today. And because the universe has expanded for billions of years, that original hot light has been stretched into microwaves, so we detect it now as a faint, cold glow coming from every direction in the sky. That glow is the CMB. So in a sense, when we measure the CMB, we're looking at the universe when it was unbelievably young. Now a big question, how does this confirm the Big Bang? Because the Big Bang model predicts a few very specific things, and the CMB matches them. Prediction number 1. There should be leftover radiation from the early hot universe. And we found it. In the 1960s, scientists detected a microwave hiss that didn't come from Earth, the Sun, or our galaxy. It was coming from everywhere almost equally. That's exactly what you'd expect from an early universe that was once hot and glowing everywhere. Prediction number 2. It should have a specific temperature. When we measure the CMB today, it's about 2.7 Kelvin, just a few degrees above absolute zero. And that number isn't random. It fits the idea of an expanding universe where light gets stretched and cooled over time. Prediction number 3. It should be almost uniform, but not perfectly. And this is where the visual maps become powerful. When you see those famous CMB maps, often shown in reds, blues, and yellows, it looks like a weather map of the early universe. But those colors don't mean hot and cold in the way we feel temperature. They show tiny differences, small variations in density and temperature across the early cosmos. And those tiny variations matter because they're the seeds of everything. They're the reason galaxies formed. They're the reason stars and planets exist. Without small differences in the early universe, matter wouldn't clump together. The universe would be smooth and empty. So when scientists study the pattern of those tiny variations, they're basically reading the starting conditions that later became cosmic structure. And this is why the universe feels measurable. Because the CMB is not just a glow, it's data. Scientists can measure the overall temperature, the size and distribution of the variations, and how those patterns match models of expansion, matter, and geometry. And what's incredible is how consistent it all is. Different satellites and experiments over decades have mapped the CMB in more and more detail, and the picture keeps lining up with the same big idea. The universe started hot, expanded, cooled, and evolved into structure. Now, does the CMB answer everything? No. There are still big questions, like what exactly drove the earliest rapid expansion and what dark matter and dark energy really are. But the CMB is one of the clearest windows we have into the early universe. It makes history visible. It turns the sky into evidence, and it reminds us the universe isn't just something we imagine. It's something we can measure, all the way back to the beginning.